So as well as denoting sets with mathematical notation like this, where we write A equals to curly brackets, the set containing 1, 0, 2, 5, and 3, as well as using that mathematical notation, we can represent sets diagrammatically with circles. And so we'll just do that now. We'll draw a circle for A, and we'll draw another circle for B. And so loosely these represent, the space which A and B covers, and sort of A contains all the stuff in this space here, and B contains all the stuff in this space here. And so this has a useful and quite immediate application where we can see that when these two circles overlap, this area here, which I've just shaded in light blue, is going to be the intersection of A and B. So the things that are going to be in this overlapping area are 2, which is in both sets, and 3, which is in both sets as well. Okay, so we can represent sets diagrammatically like that. In addition to having sets that are comprised of just whole numbers, like we constructed before, we can actually put whatever we want in a set. Because after all, remember, a set is just a collection of objects. And so we could put numbers like, 17. We can even put fractions like 3/4 or irrational numbers like pi in a set. It doesn't even have to be numbers. We can put in shapes like a star or a square. Okay. Or we can even put in a color like blue. And so there's really, to start off with, there's no restriction on what we can put in our sets. But we can sort of see straight away that it's a little bit silly to have sets containing the colors blue, stars, and squares if all we really care about are numbers. It's not really a useful thing to have. And so we define this very convenient notion of a universal set. Okay. And a universal set is a set that we define by ourselves. It's not there. We've got to state what it is. And it's the set of all the different objects or elements that we actually care about in this particular setting. So in a particular setting, we could say, okay, all the objects I care about are just these whole numbers from 0 through to 9. Okay. So the universal set, the set of all the elements that I'm going to actually allow myself in a particular situation to construct subsets with, is going to be this set here. Okay, so we can see that A and B are subsets of this universal set, but Y is not. Y is not a subset of this universal set. Y is over here somewhere. And so for our purposes, we actually don't care about Y because it's not part of our universal set, so it's not relevant for the analysis we're doing in this particular situation. And so going back to this diagrammatic setting, the way that we represent a universal set, so this is just one diagram, and this is, I'm going to draw another diagram over here. The way we represent this universal set is usually by a rectangle to distinguish it from just our standard sets like A and B. Okay. And we denote it U diagrammatically like that. And so any set of interest is going to be inside it's going to be inside this rectangle here. So I can redraw A in this new diagram here. And there it is. And I could draw B as well. And so having this universal set, having this sort of outer bound to what I'm allowed to make my sets out of, it allows us to define a very useful set operation. Okay. And this is an idea of a complement. And so we denote that A with a bar on top. And so where A is everything inside this circle here, A complement is everything inside this universal set that's not inside that circle. So it's just everything that's not inside A that we care about. So it's in the universal set. And that should sound quite familiar because we can actually use a set notation we've already learned to define this. And so we can write a bar or a complement, the complement of the set A. We can write that as U difference A because it is just this set U. We've taken a whole out of it and the whole is A. Okay. And so that's a very useful concept because this universal set allows us to restrict what we're looking at And because we're restricting what we're looking at, we have this concept of, oh, everything else, everything that's not in A. Whereas if we didn't have this universal set, this set would be just incomprehensibly big because there could literally be anything in this universal set. And so this set would contain every conceivable possible thing that was not in A. So we wouldn't even use that if we didn't have a universal set. So as well as thinking about sets diagrammatically and denoting them with lists like this, there's actually a third way we can represent sets, which can be a very convenient shorthand. So it's a sort of a quicker way of representing things. And so imagine if we've got a very complicated set with many, many elements. And we can actually denote a set like that. So let's make a new set called V. Okay. And this is going to be probably an example where we don't need to use this type of notation, but just to get you comfortable with it. And we can say V is the set of all. So X is some element. We're going to find a bit more about it. We do the set of all X, and this vertical line here, we can also do a colon like that. The set of all X such that, and then on this side here, we're going to write a couple of rules. Okay. And so we're going to write, okay, we want X to be an integer. So X is an integer. So it's a whole number. And we also want X to be strictly greater than 0 and less than or equal to 4. Okay, but in general, this is just a way of denoting some set, and we always write it like this. V is equal to the set of all things X. We could even write, all things X plus 1. So there's going to be some sort of formula here, but in the simplest case, we've got just X. And on the right-hand side of this vertical line, or this column, we've got some rules. Okay, we've got some rules. So our first rule here is that X has to be an integer. So if it's not an integer, if it doesn't pass that first rule, it's not going to be in this set V. And our second rule is that X is strictly greater than 0 and less than or equal to 4. And so if some possible X, and so we might say, oh, what about 0? Could 0 be in this set? And we've got to say, okay, 0 does not satisfy this second rule because 0 is not strictly greater than 0. And so 0 would not be in this set. And so we can evaluate this, we can write this out, and we can say, okay, well, I need to write out all the integers, all the X's that are integers that are between 0 and 4, but not including 0. And they're going to be 1, 2, 3, and 4. Okay. And so we've got back to our original way of representing a set, which is a list of elements. We can go back to this sort of rule-based way of denoting a set. And this becomes very useful later on when we don't want to be very specific about what exactly is in our set, and we want to say, oh, they're just some things that satisfy some rules.